Well, in this class, we will discuss particularly the magnetic vector potentials, the electric scalar potentials, the gauge transformations, Coulomb-gauge conditions, and Lorentz-gauge conditions. These few things we will discuss in this class. Now, to pick up with the magnetic vector potentials, if you recall our earlier discussions that the secondary differential operators, to remind you here that in the secondary differential operators we have seen certain identities, and these magnetic vector potentials and electric scalar potentials are consequences of certain identities of these secondary differential operators. Now, to select the identity, that is your divergence of curl A equal to 0. If you see to this one, that means the curl of A, which is also a vector quantity, you can write it as some another vector, let us say as B vectors, right? So therefore the divergence of curl A, which is equal to 0, can always be written as divergence of B vector, which is equal to 0. That means B is always expressible in the form of curl of A, and where your B you have got by differentiating in a curl manner the A vector. In other words, if you recall the definition of potentials, that means if your B is a field expressions, then A has to be a potentials. That means if you are differentiating the potential getting the field, so if you assign B as your magnetic field, then A has to be potentials, and it has to be magnetic potentials because you are getting B as your magnetic field, so A has to be your magnetic potentials. And obviously as per the operations, if you have seen that curl of A, so A has to be a vector quantity, so A, now we call it as a vector magnetic potential, or you say as magnetic vector potentials. Now the important thing in this discussion here is that the magnetic vector potential which we have defined, it is not unique. It because for the same B means for the same magnetic field, you have large number of choices for potentials. How? You can pick up and check that the divergence of B equal to 0 is valid when you take B to be equal to curl A. In the same manner, when you take B equal to curl of another vector M, where M vector can always be written as a composition of A vector and C vector, that means A vector plus C vector, if you choose as M vector, for that also your divergence of B equal to 0. In the same way, you can choose your B to be equal to curl of A minus grad F, where again you have chosen another vector, some N vector, to be equal to A vector minus grad F. So obviously the divergence of B, which you are getting the single defined magnetic field, generates large number of potentials. So therefore the potential is not uniquely defined, it is arbitrary. The potential A which you have got, that magnetic vector potential, is arbitrary. So that brings the necessity that we must use certain conditions to restrict the problems as per our choice, and accordingly Coulomb condition, Coulomb-gauge conditions and Lorentz-gauge conditions are such conditions. And what is that gauge? The gauge is that when you select the condition, because before applying to that condition, you must ensure that the physics remains invariant in any other forms of transformations, and accordingly we say that that is gauge invariance. If you change any other frame of reference, let us say, then the physics remain invariant, and if you have to testify that one before applying that particular conditions, in our case Lorentz-gauge conditions or Coulomb-gauge condition, before applying you must testify that the fields, electric and magnetic field to which you are applying, it remains invariant, and that is you say as gauge transformations. It has to be remain invariant under gauge transformation. And well, you can check it also. That means when you go for in the same way, when you go for the electric scalar potential also, you can say that your curl of grad phi equal to 0, which is also an identity in the second order differential operator when we are discussing, it is always true. So therefore curl of grad phi means that the grad phi which is a vector quantity, so you can write that grad phi as equal to some another vector, let us say E vector, and it is E you can write as grad phi with negative sign. Here we choose to write the negative sign, it is because if you recall the definition of potential gradient, that is how do you define the potential gradient in one dimensional? In one dimensional it is E equal to minus del V by del X. So if you recall to that definitions, it is actually the outcomes of these general transformation equations that E can always be written as negative of grad phi. So here also when you differentiate this potential phi in a grad operator, it is operating, that is giving rise to field, which we say in this case electric field, and obviously it is electric field, so therefore phi has to be electric potentials. And the grad when it is operating without using any dot or cross obviously, so therefore the phi has to be a scalar quantity, so we say it scalar electric potentials, or you say it electric scalar potentials, either of the choice. Now this phi which is you say is electric scalar potential, in the same manner how we have seen already the magnetic vector potential A vector is arbitrary, this phi is also arbitrary, that means it is not also uniquely defined. You can check this one by selecting Maxwell third equations. What is the Maxwell third equations? That is curl of E plus del B by del T equal to 0, and you can always replace the B vector, magnetic field vector, by writing curl of A as we have seen. So therefore now you can write curl of E plus del by del T of curl of A equal to 0, and this grad being a space part, you can take it outside common and then write it curl of within bracket E vector plus del A by del T has to be equal to 0, and this within bracket what you are writing, that is E vector plus del A by del T, that place you can write grad phi because it has to be a vector quantity, so therefore you can write of grad of phi. So therefore that if you compare this expression, that is curl of E plus del A by del T equal to 0, you can compare with the identity from which we have started for this scalar electric potentials, that is curl of grad phi equal to 0. So therefore here you can write your grad phi in place of within that bracket E vector plus del by del T of A vector, where your negative of grad phi has to be equal to E vector plus del A by del T vectors, because recalling the definitions that here we take the potentials as definitions, we set the concept and the work done we start, or we assign the work done at infinity to equal to 0, so therefore we put a negative signs, that is work done against the field, you are bringing the body from infinity to this point persons, so right, that is why you are using the negative signs. Now if you rearrange this minus grad phi which you have written minus grad phi equal to E vector plus del A by del T, you can write it E vector as equal to minus grad phi minus del by del T of A vectors. Now in place of A, since A is A, what is A? A is magnetic vector potential, and we have seen magnetic vector potential is non-unique in nature. So therefore in place of A, you can always write something grad of another F, where F is a scalar quantity. Now if you write that way, then E vector can be written as equal to minus of grad phi minus del by del T. In place of A, you can write grad F. So therefore now if you take the space part, that is grad outside, so you can write it as a minus grad within bracket phi plus del by del T of F. It is because your space part grad is independent of time, and what is this within bracket, that is phi plus del by del T of F, that place you can write down it as phi prime. That means whenever you can write your phi prime to be equal to phi plus del by del T, del by del T, in that case your same the identity will hold. That means again your phi when transferred as phi prime, that identity is valid. So therefore, like the case we have discussed, we have so many choices for the same field as like that of your A plus C vectors, or you can have your A vector minus grad A vector for the same field, generating same field in case of your magnetic vector potentials. In the same way here, when you select phi prime to be equal to phi plus del F by del T, del F by del T, in that case this identity is valid, so therefore the electric field which you are getting can be generated out of as many number of electric potentials, of course scalar electric potentials, and it is because if del F by del T can be many. You can have del F1 by del T, you can have del F2 by del T, like that you can have. So therefore your phi prime can take as many number of possibilities. That is how your phi is also not uniquely defined. Now by now you know that your A vector, which we say is magnetic vector potentials, and your phi, which we say is scalar electric potentials, both are non-unique in nature. So here the essentiality is that before we apply to solve these potentials, like we are applying in various cases, we must test the invariance of this field. So therefore we will discuss now what is Gauge transformations. And Gauge transformation actually is a set of transformation under which your electric and magnetic field remains invariant. How? In this case we can pick up one case and discuss it. Let us check for electric field E. Now when electric field transforms as E prime, you can write always as E prime equal to within bracket minus grad phi prime minus del A prime by del T. And in place of phi prime, you have to use the transformations, that is phi prime equal to phi plus del by del T of F. So in that case I can write that is minus grad of phi plus del F by del T, where I have replaced phi prime with phi plus del F by del T. And the second term minus del by del T, in case of A prime, I will replace as that of your any of the choice, and here I select the third choice, that is A minus grad F. So if I use in place of A prime as A minus grad F, the second term will become minus del by del T of A minus grad F. And therefore my E prime vector will be equal to now minus of grad F, opening the bracket of course, minus equal to minus grad F, grad phi, minus grad of del by del T of F, and the third term becomes, which is the first term of the second term, that is del by del T of A vector plus del by del T of grad F. So these four terms we have got. Now if you see to the second and fourth terms, that means the time and space, they can exchange each other. It is because they are independent of each other. So therefore you can take out one outside and see that both of them are same. So therefore you can cancel them. Now what remains is the first term and the third term. So therefore E prime vector can be written simply as equal to minus grad phi minus del A by del T. So taking out common again that of your negative, you write it is the same E equal to minus grad phi del A by del T. So we have started from E prime and we have now reached at E vector. So therefore under these transformations we have seen that our electric field remains invariant. In the same way you can pick up for B vector also. That means when you pick up the B vector, how do you write under transformations? That is B you write as curl of A. So when you write B prime, that has to be equal to curl of A prime. Now what is A prime? Again you have three choices or so many choices in fact, and out of that in our discussions I will select the third choice where I have taken my A vector to be equal to A vector minus grad of phi from scalar. So therefore in case of my curl of A prime, I will replace my A prime as within bracket A vector minus grad F. Now what will happen? I will open the bracket again and that I will write my B prime equal to curl of A minus curl of grad F. Now if you see this curl of grad F, it is again 0 by the same property we have started from. That is the one of the important property where we have started, that is second order differential operator, that is curl of grad phi of any vector is always 0. So second term therefore vanishes. Now what remains is curl of A. So we have started from B prime and you have reached now with B vectors. So therefore, if you use these transformations set of equations, that is when A transform as A prime, where A prime can be written as A vector minus grad f, and phi transform as phi prime, where phi prime equal to phi plus del f by del t. Under such transformations, your electric and magnetic field remains invariant. Now this is essentially a required condition before you apply to solve some potentials in some of the selected cases. For example, in your Lorentz and CoulombGauge conditions. Why such conditions is essential? It is because we have seen that your potentials, electric and magnetic potentials, in both the cases, both of them are being arbitrary. You have a large number of choices for the same field. That means you are getting so many potentials to differentiate and get this same B vectors, I mean field vectors. In case of magnetic potentials, same magnetic field. In case of scalar potentials, that is scalar electric potentials, you get electric field. You differentiate so many possibilities to get the same values. So therefore, to restrict this arbitrariness in the potentials, you need to put certain conditions so as to identify the exact physics how the potential exists actually. So in that case, this arbitrariness is selected choice and we use some of the conditions. In few examples here we will mention, which we frequently discuss in electromagnetism, is your LorentzGauge condition and CoulombGauge conditions. What is essentially required in a LorentzGauge condition is a divergence of A plus 1 by c square del by del t equal to 0. This is a LorentzGauge condition. That means if you use these conditions, you will get a certain group of potentials that will be identified as a group of physics. So we will restrict the arbitrariness in the potential by using this LorentzGauge condition to identify a group of potentials conditionally. Now in the same way, we can also limit the arbitrariness by using the CoulombGauge conditions, which is divergence of A equal to 0. Like that, we can restrict these arbitrariness in the potentials depending upon each of the problems. And you can also put your conditions. If you are working over it, you can put your conditions to identify some kind of potentials or to assign some of your physics to get the same field expressions. Now these extensions of these potentials we can apply to that of your Maxwell's equations also, where we are writing the electromagnetic wave equations in terms of potentials. And in our second class also we can discuss regarding how we can apply this potential to write the electromagnetic wave equations in terms of these potentials. Thank you.